Welcome to the Deep Dive. We're the place you come to take a stack of sources, really dig in, and get properly informed. Today, we're zooming in on a material you've probably bumped into, maybe even walked on, countless times without realizing it. Polymer wood fiber composites. You'll hear them called WPCs. So our mission really is to pull back the curtain. What are these things, these sort of hybrid materials? How do you actually combine wood and plastic effectively? And where are they popping up? Sometimes in surprising places. And maybe most importantly, why are they such a fascinating blend of, nature and tech? It's really a story about smart material problem solving.
That's a really good way to frame it, yeah. Because at their heart, WPCs are these pretty ingenious hybrid materials. It's basically a clever mix. You've got natural wood fibers, could be recycled, and sawdust, wood flour, that kind of thing. And you combine that with thermoplastic polymers. And the genius, like you said, is the design intent. They're made to give you that look, the feel, even the workability of wood.
Right, the familiar stuff.
Exactly. But you get the durability, the moisture resistance that you expect from plastics. And that combination, it's why they've just surged in popularity over the last, say, 20 years. Big advantages in sustainability and performance.
Okay, so when I first heard about this, I was thinking wood, plastic.
Mm-hmm.
How do you even start to, combine them? Can you break down what WPCs are made of, like, fundamentally?
Yeah, it's a great question. It really is a synergy. So imagine taking the essence of wood, right? Natural fibers, maybe even really fine wood flour, and you blend that very carefully with thermoplastic polymers. These are common plastics, often recyclable ones like polyethylene, polypropylene, PVC, stuff like that. But it's not just chucking them in a bucket together. It's carefully engineered so the two materials actually bond. They create something new that has properties better than either one alone.
And the why. That's where it really clicked for me, too. It's not just mixing for the sake of it. It solves problems, right? Like anyone who's dealt with wood outdoors, the rot, maybe termites, constantly having to sand it, stain it. WPCs seem like a direct answer to that.
Precisely. Yeah. You're leveraging the best bits of both. From the wood, you get that warmth, that look, the feel, and you can work it, right? Cut it, drill it, use standard tools. But then the plastic side brings incredible resistance. Moisture, rot, decay, insects, all the things that typically attack wood. So that's the magic, like you said, marrying that natural aesthetic with synthetic resilience. Yeah. You end up with something way more versatile and honestly requires a lot less maintenance.
Okay, that blend sounds incredibly smart.
Yeah.
But how do they actually make it? How does manufacturing turn wood dust and plastic pellets into, a deck board? I always find that industrial alchemy part fascinating.
It is fascinating, and it's a very controlled process. Super important for consistency. So it usually starts with raw material prep. This means drying the wood fibers or flour really well, grinding them down to a fine, consistent powder, and at the same time selecting the right thermoplastics. That depends on what the final product needs to do, High weather resistance for decking, maybe different properties for a car part. Then comes the crucial step, mixing, or compounding, as it's often called. Here, the wood fibers and polymers get blended together. But it's more than just mixing. You almost always add in various additives. Lubricants, maybe, to help it flow during processing, stabilizers for UV protection, colorants, obviously, and really importantly, something called coupling agents. Think of them as molecular glue. They make sure the wood and plastic actually bond strongly together. That's vital for the final strength and durability.
Ah, okay, that makes sense. The glue part.
Exactly. So once you've got this uniform, well-mixed compound, it goes into forming. Usually extrusion or injection molding. Extrusion is for long, continuous shapes, like deck planks, fence posts. The material gets pushed through a shaped die. Injection molding is different. That's for smaller, maybe more complex parts. You inject the molten composite into a mold. It cools quickly. Think maybe small components, housings. Both methods aim for a uniform, moldable composite with those engineered properties locked in. And then finally, it's cooling and cutting. After it's formed, you cool it down, cut it precisely to size, maybe some finishing touches, and then it's ready to go. A real testament to modern material science, actually.
That really clarifies it. It's like a very specific recipe. So with this carefully made material, where are we actually seeing WPCs? You mentioned decking, but where else are they popping up? Because, like you said earlier, you might be surprised how common they are. That weather resistance, the workability, the low maintenance must make them pretty useful.
Oh, absolutely. They're incredibly useful. So in construction, like we touched on, they're huge. Outdoor decking, that resists rot and splinters, but also exterior siding cladding that you never have to paint, fencing that lasts ages, railings, even things like window and door frames that had to stand up to tough weather. Anywhere, durability and weather resistance are really key.
Right, makes total sense for outdoors.
But it's not just outdoors. The automotive industry uses them quite a bit now. Interior trims, panels, dashboards, they offer a lightweight, often more sustainable option, sometimes with a nice feel too.
Interesting. Inside cars.
Yep. And then furniture, especially outdoor furniture, obviously, but also things like cabinetry, shelving, again, capitalizing on that resistance to moisture and wear. And you might even find them in everyday consumer goods. Look closely at some tool handles, maybe some kitchenware, certain kids' toys, housings for electronics. It just shows how versatile they really are, things we use constantly.
It's actually quite remarkable how they're sort of quietly improving so many things around us, making them last longer, maybe need less fuss. Okay, but like we always say, no material's perfect, right? WPC sound great, but there got to be trade-offs. We've talked up the advantages. Let's get into the full picture. What are the limitations?
Absolutely, always good to have the balanced view. Starting with the advantages, though, they are compelling. First, sustainability. That's a big one. They often use recycled wood fibers, recycled plastics, which helps reduce landfill waste, promotes that circular economy idea, and means less reliance on new timber. Then, durability. We've hit on this, but it's worth repeating. High resistance to moisture, insects rot, decay. They just last a long time, especially outside.
Which leads to the next one, I guess.
Exactly. Low maintenance. For most people, this is huge. Generally, no need for painting, staining, sealing. Saves a lot of time and hassle compared to traditional wood. And for builders or DIY folks, the workability is a plus. You can cut them, drill them, fasten them just like wood using normal tools. Pretty straightforward. There's also design flexibility. Because they're molded, you can get complex shapes, consistent quality, consistent color, opens up design options. And finally, weather resistance, handles hot, cold, wet conditions really well. Ideal for outdoors.
Okay, those are some strong points. Definitely see the appeal. But, like you said, the trade-offs. What are the things engineers or designers or even us as consumers need to keep in mind? What are the cons?
Right, the other side of the coin. Well, for one, they can have some mechanical limitations. Compared to, say, solid structural plastics or metals, their strength and stiffness might be lower. You wouldn't build a whole bridge out of them, you know. There's also thermal sensitivity. WPCs tend to expand and contract with temperature changes more than wood does, so you need to account for that in installation. And they might not be suitable for really high heat environments consistently.
Right, expansion gaps and things like that. And I heard they can be heavier.
That's often true, yeah. Higher density. They can be heavier than regular wood, sometimes heavier than pure plastics too. Might matter where weight is critical. Though, interestingly, that density can sometimes feel reassuringly solid underfoot on a deck, or help with sound dampening. So it's not always a pure negative.
Okay. Nuance.
Nuance, exactly. And related to moisture, while they're generally resistant, there's the moisture sensitivity of the fibers themselves. If the manufacturing wasn't spot on, if those wood fibers aren't fully encapsulated by the plastic, they could potentially absorb some water over time, leading to maybe swelling or warping. Good quality WPC design minimizes this, but it's something inherent to the composite nature. And lastly, cost. Sometimes the initial price tag for WPCs can be higher than standard timber. You really have to do that cost-benefit analysis, weighing the upfront cost against the long-term savings on maintenance.
That really does raise that important question then.
Yeah.
How do these pros and cons dictate where WPCs make the most sense? Understanding those limitations is clearly key to using them effectively. What's really fascinating now, though, is that this isn't a static field. WPCs are still evolving, right? Researchers, companies, they're pushing things forward. It feels like we're seeing constant innovation.
Oh, absolutely. It's a very active area. The innovations are pretty exciting. For instance, there's a big push towards using bio-based or biodegradable polymers. Think PLA, PHA. Plastics derived from plant sources instead of fossil fuels. This is huge for reducing the environmental footprint even further, making them even more sustainable.
It's a significant step.
It really is. Another big area is nanoadditives, adding tiny, tiny amounts of things like nanoclays or cellulose nanofibers into the mix. These can dramatically improve strength, stiffness, even barrier properties, making the WPC tougher, more resistant. We're also seeing continuous improvements in advanced surface treatments and those coupling agents we talked about. Better bonding between wood and plastic means better performance, especially in really demanding conditions. Longer life, more reliable.
And what about making things with them? Any changes there?
Yeah. 3D printing with WPCs is starting to emerge. Imagine being able to print custom WPC parts, complex shapes with minimal waste. That's a potential game changer for specialized designs, prototyping, maybe even small-scale manufacturing.
Wow, okay. Custom WPC parts.
And finally, there's just a relentless focus on recycled content integration. Constantly finding ways to use more post-consumer plastic waste, more wood waste, really closing that loop and boosting the circular economy aspect, giving old materials a high-value second life.
These aren't just small tweaks, are they? They feel like fundamental improvements that are really setting WPCs up for the future, making them even more viable, more sustainable. It's exciting stuff. So as we wrap up this deep dive, it's really clear that polymer wood fiber composites, these WPCs, they're a genuinely compelling material choice for so much modern engineering and design. They hit that sweet spot, don't they? Especially where you need sustainability, durability, and good aesthetics all rolled into one.
Exactly. And it's worth saying again, with all the ongoing innovation we just discussed, better materials, smarter processing WPCs aren't just sticking around. They're poised to play an even bigger role globally. That whole shift towards greener, smarter materials, WPCs are right in the thick of it across tons of industries.
Yeah.
Their potential to blend, the best of nature with human ingenuity, it's really only just beginning to be fully realized, I think.
Which leaves us with a final thought, something for you to chew on. Considering how fast WPCs are advancing, how versatile they're becoming, how might these materials reshape not just our buildings and products, but maybe our whole approach to using resources and managing waste in the coming years? Just imagine the ripple effect on industries that have relied solely on timber or pure plastics for decades. What could that future look like?